All right, today's goal is to be able to take a word problem that is a calculus problem in context, set up an equation for it, use some calculus on it, and come to a solution and answer the question. So these are a lot of word problems, and how many people love word problems? Okay, 2 of you, awesome. Uh, Words get in the way sometimes. This is the kind of thing you'll see a lot, at least the problem in context, you see a lot on AP exams. I want you to know that once you can get these problems set up, the work is the same as the work we've already been doing. We're going to use max-min existence theorem. We're going to use the first derivative test. We're going to use the second derivative test to verify our answers. The first example here is a pretty classic mathematics problem. We're talking about a rectangular box that's going to be made into some sort of, a rectangular box to be made from a piece of cardboard. You're going to take a piece of cardboard, you're going to cut a square out of each corner, you're going to fold up the sides, and you're going to have a box without a top on it. Anybody seen a problem like this before? Like 2 of you? Some of you nodding. Pre-calc did problems like this, didn't they? The difference between calc and pre-calc is in pre-calc, you were allowed to use your calculator to make a graph of the function and find where it was at a max. In calculus, we're probably not going to have the benefit of a graphing calculator. So we're going to have to do this kind of the by hand way. But we're going to use the idea that we already know what a maximum is, right? How do you find a maximum? A maximum is you set the derivative equal to 0, you find the stationary points, use the first derivative test to verify. We'll go through all this step by step in a moment. Use the first derivative test to verify that's a max, or use the second derivative test to verify that it's a max, or you can use the candidate theorem, which we talked about briefly, and I'll mention it again today. But you need to, in some way, defend the fact that you got a maximum. That's where most of the points are going to be assigned on the AP exam, because there's a lot of ways to get the answer to this, but the points are going to be assigned to defending your work. So that's the theme for today. So what we need to do here, I'll give you a little recommendation here. Whenever you have some sort of optimization problem and it's asking you to maximize or minimize something, I like to put a circle around really important words or a rectangle around really important words. You want maximum volume. So what it really comes down to is you're going to find an equation for volume and you're going to set its derivative equal to 0. So we need to start with identifying some variables and then coming up with the equation for volume. So we're starting with, and the picture here is a 24 by 9 piece of cardboard. We're going to cut a square out of each corner, and we're going to fold up those edges to make a open-topped box. So this side starts, we'll kind of go by scale here. This side starts at 9, that side starts at 24. The thing that is going to vary is the length of the edge of the square. That's going to be our variable here. Okay? If it helps you, you can write out the old geometry formula for the volume of a box. 3 dimensions on a box, many people would write LWH or some combination of those 3 letters. Okay? So the dimensions of our box need to be put in terms of one variable. We cannot, this is not an implicit derivative unit, so we can't have that many variables. We're not going to do dt, dt's, and dv, dt's, and all that kind of stuff for this type of problem. So we need all of our dimensions, the length, the width, and the height, in terms of one variable, and we're going to call that variable x. I'm going to put an x up here on my picture. I recommend you do the same. All of these edges will be x, which will really only represent one dimension when we fold up the edge of those boxes, or the sides of the box. All right? So, in terms of x, what will one of the dimensions be? Let's start with this. I'll pick one. I'll be more specific. What will this length turn into when I fold up 2 edges? 24 minus 2x. 24 minus 2x. Okay? What will this dimension turn into? 9 minus 2x. And then the third dimension will be the length of the square taken out, right? This will be x. Okay? So now if you were in pre-calculus, you would take that function, you'd put it into your graphing calculator, you'd find the max, you'd make sure it made sense, and then you'd move on, right? We need to do this in a little bit of a different way because we have to use calculus on it. Graphing calculators put away for the moment, okay? Now, once we have an equation, and this is the order I like to do things, you can do things in a different order if you'd like. Once we have that equation for volume, I recommend considering what domain values would be appropriate, okay? And the reason for writing down appropriate domain values is I'm going to go back to the extreme value theorem. Remember extreme value theorem? If the function is continuous and it's on a closed interval, we can guarantee that there will be a max and a min. And if I can verify that it's continuous on a closed interval, I don't need to do a lot of calculus. I'm going to show you the calculus, and I'm going to show you really have three options to verify this answer. But we're going to look at the domain. What is the smallest acceptable value for x? 0. 0 is the smallest acceptable value for x. Could it, like in theory, I know it's weird in a real life context, but could x be 0? You wouldn't really be cutting a square out, but from a modeling standpoint, it could be. What would the volume be if x was 0? 0, because you wouldn't have that third dimension for the box, right? Okay. What's the biggest x could be? 4.5. Where are you getting 4.5? If we fold up 4.5 off here and 4.5 off here, the cardboard is completely folded in half. How much volume is there? None, right? Okay, so there's a good chance that since on the left end of the interval the volume is 0, and the right end of the interval the volume is 0, that the max is going to occur somewhere in the middle, right? Okay. We'll talk about that more in a minute. But I think it's significant to write down what the domain is to know what kind of answer you're looking for. Okay? Let's do some calculus now. Do you want to do the derivative of that as it sits? Do you like it? Or do you want to change it? Change it. What should we do? Let's FOIL the thing and distribute the x. You do, I'll do, we'll do it at the same time. Okay, go. Let's go ahead and now we have that volume equation simplified as a polynomial. It's a cubic polynomial, so don't forget about what you know about cubic polynomials. It's a cubic polynomial with a positive lead coefficient. It probably does something like that, probably. Okay. Let's do v prime. 4x cubed, the derivative of that is 12x squared. This gives us 66x squared, gives us 132x, and that gives us 216. This gets a little bit tedious without a calculator, but I think it's doable with a little bit of mental math. We're going to set that derivative equal to 0. Why are we going to set the derivative equal to 0? Find the stationary point. Because we have a closed interval. We have a continuous function. How do we know it's continuous? What type of function is it? It's a cubic. It's a polynomial function, right? Are polynomial functions continuous? You bet. It's a closed interval. How do we know? We decided that that's the domain. Okay? So really, now the candidate theorem, I don't know if this was an official theorem, but I call it the candidate theorem. Candidate theorem says that we know the max and min are going to exist because of these two qualifications. The candidate theorem means all we really need to do is check the endpoints and the critical points. Okay? I have no idea what that was. I thought I had this thing password protected. I had it shut off. I'm gonna take just a moment and do that. All right, let's resume. Okay, so we need to set that quadratic polynomial equal to 0. What do we have to do here? Gosh, it would really be nice if 12 came out, wouldn't it? Does it? Let's take out a 12. Let's see what happens. If we're wrong, we can just try a different method. But if 12 comes out, is 132 divisible by 12? It's got to be, because 144 is divisible by 12, and that's 12 less than that. So that's 11x, right? Is 216 divisible by 12? Somebody said 18. Yeah, I think that's 18. So this ends up being nice. And they kind of have to be, guys. If calculators are not allowed, they kind of have to be nice. These aren't the nicest the numbers could be, but it works. We've got x minus 9, x minus 2. We have two critical values, x equals 9 and x equals 2. Those are two stationary points on this graph. Now, I think it's important that we did the domain earlier, because the domain is going to help us filter this right now. Which one of those is a good idea? X equals 2. Which one's a really bad idea? 9. 9's not in the domain. You can't fold up 9 inches off of both sides of a side that's only 9 inches long. Okay? So you don't need to do a lot of defending here, but this one's no good. All right? Now, I think based on what we know, we're all really confident that at x equals 2, the graph's going to have a maximum. But just knowing it's not good enough, you have to defend it. So here are your three options. Okay? And I'm only going to finish with one of them, but here are your three options. You can use candidate theorem, knowing that the answer for the maximum question is either v of 0, v of 2, or v of 4.5. Okay? V of 0, we already agreed, was 0. V of 4.5, remember that piece of cardboard would be folded completely in half? Would we have volume? No. What's V of 2? Well, we can go back up here and do it. V of 2 is 24 minus 4, that's 20. 9 minus 4, that's 5. And x is 2, so that's 20 times, that 200? Okay. Would this be enough? I think so. There's your maximum volume right there. Okay? Now let's just say that these were hard to calculate. Here are your other options. Number 2. Oh, number 1, the candidate theorem. Number 2 is the first derivative test. And number 3 is the second derivative test. Just to refresh, and I won't do all three of these on all the problems, but just to refresh the first derivative test and the second derivative test, because we haven't done a lot of examples on it, the first derivative test says this. You take a number line, and you put your critical values on it, 2 and 9, and then we check v prime. What's v prime? There's v prime. 12x squared minus 130x plus 216. What's v prime of 0? 216, right? It rises. You got a positive derivative to the left of 2. Okay? Let's do v prime of 3. And I'm actually going to do it in there. V prime of 3 is 12 times negative 6 times 1. Negative or positive? Negative. It's going to fall in that region. We knew that, though, guys, didn't we? We're just defending what we did. Okay? So, and we already knew that 9 was a bad idea, so we're not even gonna go with that because it's not part of our domain. So now we could say that x equals 2 is a max because v prime changes from positive to negative. That's a valid response. That's a valid defense of the fact that x equals 2 is a max. Good so far? Do you have to do all three of these options? No. You need to pick one. Okay, I'm giving you all three on the first one. We won't do all three all the time. Okay? The third option is the second derivative test. And for polynomials, this one's my favorite. What's the second derivative here? Is it easy or hard? Easy, because it's polynomial. Second derivative is 48x minus 132, isn't it? Second derivative. We just differentiate those two. I guess we could differentiate the 216 too. But 48x minus 132 is v double prime. V double prime, 48x minus 132. What point do we care about the second derivative at? X equals 2. So v double prime of 2, 48 twice is 96, right? That's 96 minus 132. I don't really care what that number is. Don't stress yourself out about subtracting 96 minus 132. Don't worry about it. Because we know now that v double prime of 2 is less than 0. Sad face, right? Which means that x equals 2 is a local max. Okay, now that's a lot of work, guys. I did 3 methods. You don't need to do all 3, but I want you to see what justification is valid. Okay? Please, once you've gone through the justification, make sure you answer the question. Got a question here. Okay? Where did I get 48 for the second derivative here? Is it supposed to be 24, guys? I'm sorry. Should have been 24. Good question. Either way, good call. 24x minus, so 24 times 2. This is 48 minus 132. Still negative. Thank you for clarifying that. Okay, another question. That very last step. Sure. Okay, great. It's the question is just to verify the last step. We know, number one, we know that v prime of 2 equals 0. So we know that it's a stationary. So once we know it's a stationary point, it's got to be one of these, or one of these. Okay? Once we know that it's one of those 3, the value of the second derivative can help me determine it. So since I know that v double prime at that point is less than 0, I know that I'm in concave down territory. So the first derivative is 0, the second derivative is negative, so it's concave down, which those two together tell me that it's got to be a maximum. Okay? Good. I kind of skipped that first part of the verification, though, because I had done it twice already. Okay? Now, once you've done the calculus and the defending, please go back and make sure you answer the question. Find the dimensions of the box, and what is the volume? Okay? We already kind of did the dimensions, didn't we? We did the dimensions. We were doing this up here when we were calculating the volume there. The dimensions are 20 by 5 by 2. So down here, we'll just go dimensions would be 20 inches by 5 inches by 2 inches. And the max volume is 200 cubic inches. My picture is a little more complete than yours, so I think you probably need to label that side X on your notes. But it's a classic area example. When I say classic, it's one of those that shows up in a lot of different places. I think it's worth noting that if you have if you're allowed to make any shape field you want, and you have a length of fence, you know the ultimate shape to maximize your area. Square under the restrictions that it has to be a rectangle, a square is best. But circles are better. If you're not limited by any shape, a circle will always maximize the area of an enclosed region. If you can make a circle, make a circle. But in this case, we're not allowed to make a circle. We have to make rectangles. Now, if you were just making a rectangular field, it's worth knowing that a square would be better than any other rectangle. And I think you could draw some out and convince yourself of that. But let's do a little calculus on this, because this one has this additional length of fence in the middle, makes it so that a square is not completely appropriate here. Okay? So the length of fence that I have is 10 meters. Of course, 10 meters is a good length of fence. I think it's also worth circling or rectangling area is a maximum. So really, ultimately, if we want to maximize area, we need an equation for area. So we should start with that. Let's say area equals, and we've got our picture labeled already. So what is, based on the picture that's drawn, what is the total area of the enclosure for which I get to plant cucumbers, peppers, tomatoes, and green beans? 2x? 2yx, okay? 2yx or 2xy. I like x first because the alphabet makes more sense to me that way. Problem is we have too many variables. This is something that we're not going to differentiate implicitly. We're not going to do dy dx's and dx dx's on this. We need a way to get rid of a variable. And the other information is given to us in the sense that we're only allowed 10 meters of wire. So I like drawing on the picture to see where I need fence. I need fence here, 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 and here. That's 4 y's, right? 4 lengths of fence with length y. And I need 3 lengths of fence with length x, and that total fence is going to be 10. Okay? Because we're maximizing area, it's fair to assume you're going to use all the fence. If you didn't use all the fence, you would not be maximizing the area, I promise. Okay? We'll then go ahead. I like solving for y. I like x's better than y's. That's just the way it is. So we'll get 4y by itself. We'll divide by 4, and we'll get 10 minus 3x all divided by 4. And then that goes up into our area equation. Okay. It's also at least worth considering at this point, and I typically do this once I get the equation that I want to maximize, think about domain. Since we have x's in our function, what's the smallest x could be reasonably? 0. Would it give us any area? Nope. What's the biggest x could be? It actually can't be 10. Because if x was 10, this would be 10, and this would be 10, and this would be 10, and that would actually be 30 meters of fence. Yeah, 3 1/3 or 10/3. There was another 10 meters of fence. What now? It's not a lot for a garden. Yeah, you're right. You're right. Not a lot. Right. I need more fence. Let's go back to the store and get more fence. Then we'd have to start the problem over, so we won't do that today. We'll use what we're given, as limited as my garden will be now. All right. You want a derivative of it? Do you want to derivative it? Do you want to derivatize it? Do you want to find the derivative now, or do you want to simplify? Let's simplify first. You could, but let's simplify it. I'm going to go ahead, and I've got a 2 on top and 4 on the bottom. I'm going to make that a 1 and that a 2. I think that's going to make things a little easier. So it's going to be 10 times x over 2, more popularly known as 5x, and negative 3x squared over 2. We'll call that 3/2 x squared. There's our area function under the constraint of that domain. Okay? Trying to maximize, so what should we do? I already told you what we're going to do. We're going to take the derivative. A prime is 5 minus 3x, right? Worth noting at this point, yeah, when I differentiate the 2 goes. Worth noting at this point, if I go back to my original area function, I like kind of thinking about what this is going to look like in my own mind. I know that my area function is an upside down parabola. Is it going to have a max? Yep. Could I have done this with algebra? Sure, but it's an AP Calc problem on an AP Calc exam, so the algebraic working is not going to be enough. You need to be able to show that you're using a derivative to solve this problem. Right? But there are other methods. As soon as you know it's an upside down parabola, if you know a quick way to find the vertex of the parabola, do it. But know that you need to do the calculus in order to get all the marks. Okay? Or all the points, whatever you want to call them. So set the derivative equal to 0, and x has to be 5/3. Is it a max? Of course it's a max. It's on an upside down parabola. But do we have enough work yet? We need to defend using calculus why 5/3 is a max. Can we? We could use the candidate theorem, we could use the first derivative test, or we could use the second derivative test. Let's do the second derivative test, because this second derivative, in my opinion, rocks. What's the second derivative? -3. The second derivative is always -3, which makes sense. It's an upside down parabola. Of course the second derivative is negative, because an upside down parabola is concave down always, right? It's an upside down parabola, always concave down. Good. So since a double prime of 5/3 is less than 0, x equals 5/3 is a maximum. You can put in the word local if you want, but that's going to maximize our area. Okay? So the dimensions are x equals 5/3 and y equals, I got to put 5/3 in there, 10 minus 3 times 5/3 all over 4. That's 5/4, and these are in meters. There's our dimensions. And if it asked for the maximum area, you could do the maximum area there as well. Questions on that? Okay, we got one more to do quickly. I'll leave the bottom of that up so you can see it at the end. All right, last one. Find two non-negative numbers whose sum is 10, whose product is a maximum. We're trying to maximize a product. Okay, two non-negative numbers. Let's let x and y be two non-negative numbers. Okay? The product, we'll call it P. The product is x times y. That's what I want to maximize. I need P prime. But x and y are too many variables. What else do I know about x and y that will help me get rid of one of them? Add up to 10. Your sum is 10. So x plus y is 10. So y is 10 minus x. And our product is then x times 10 minus x. And at this point, let's talk domain. What's the smallest x could be? 0. Why? It's got to be non-negative, so it's got to be at least 0, right? What's the biggest x could be? 10, because y can't be negative either, right? And they got to add up to 10. So x has to be between 0 and 10. Okay. Let's simplify here. P is 10x minus x squared. Again, guys, upside down parabola, right? Is it going to have a max? You bet. It's probably not going to be at 0. It's probably not going to be at 10. It's probably going to be somewhere in the middle. P prime is 10 minus 2x, set it equal to 0. 10 equals 2x, and the x value is 5. Are we questions? Go ahead. It's an upside down parabola, so there's going to be a max, and the max is at the vertex. Go ahead. Another question, or is that answer it? Does that make sense? Okay. Now, are there other ways to find the vertex of the parabola? You bet, but they don't involve calculus. Okay. So how do we verify that x equals 5 is a maximum? You can do the candidate theorem. You could do the first derivative test. You can do the second derivative test. My favorite, if you can do it, is P double prime. P double prime is -2, right? So T double prime of 5 is less than 0, which implies that x equals 5 is a local maximum value. And on that closed interval, between 0 and 10, there's no other place that's going to be bigger. So x equals 5 and y equals 5 is your solution to that problem. Okay? I'd like you to work on 4.4 problems. Got the blue sheet yesterday. If you need a blue sheet, I'll get you one. But I'd like you to work on the 4.4 assignment. Do you have it, or do you want me to write it up here? Okay. 12, 13, 14, 16, 24, 39, 32, AB, and 61A.